Hello everyone, 안녕하세요. I'm Yan Tong from the School of Information Science and Engineering, Shandong Normal University. The second author is my PhD supervisor, Vasilis Frederikos, who is from the Department of Engineering, King's College London. We also had an industrial collaborator, Sebastian Andrews from Hall Robotics. This research is partially funded by UK ANIARA. I joined this project when I was a PhD student in King's. In this video, I'm very happy to represent our research group and present our work on the IoT and Sensor Networks Symposium, ICC 2022. The topic of this presentation is a Minmax utilization algorithm for network traffic scheduling of industrial robots. I'd like to share our research in the following order. First of all, I'd like to talk about the motivations. We know that industrial automation plays a critical role in today's manipulators, especially during the COVID-19 pandemic. Automatic robotics are used on assembly lines to reduce infection risk for human workers. With the advent of 5G, emerging cloud-native industrial virtualized networks with network slicing are expected to support the deployment of robotic-based manipulators. However, one of the problems in this area is that cloud-aided robotic manipulators might entail a significant volume of traffic due to the multi-sensors and multi-modules. So in this video, our proposed work capitalized on the pseudo-deterministic and repetitive nature of the robotic process to optimize the communication processing. Then I'll use the following instance to further illustrate the traffic scheduling issue in industrial productions. As shown in the right panel, for example, the robots could be dedicated to welding parts, another to polishing those parts, and the third to placing them on pallets. Each of these processes can actually be broken down into subtasks. For example, the welding robots can be broken down into part localization, then weld and quality assurance repeated for each junction. Throughout the localization process, certain data will be monitored constantly, and the data requirement is normally between 50 and 100 kilobits per second. During each weld pass, the robots will move relatively slowly, and they use a seam tracker to ensure the welding torch follows the junction between two parts exactly. This equals to an additional 1,650 kilobits per second of data. This data would be sent to analysis and log. During the subsequent quality assurance process, the same tracking sensor will take many more measurements, which produces approximate 65 megabits per second traffic flow. And the other end of the spectrum is the palletizer, which may be moving for 5 seconds to pack a part, during which intensive data transfer, that is the 65 megabits per second here, is required for computer vision. If this process runs concurrently with the quality assurance pass, we need to handle 130 megabits per second, while if it runs during the welding pass, our peak data rate is 66 megabits per second. Scaling up from this simple pair of robots, when many of these or similar processes are run concurrently, intentionally misaligning the most data-intensive tasks allows for more consistent network performance. In other words, we can flatten the data rate curve and guarantee a smooth transportation. Now let's move to the mathematical part. For each time slot, we are only interested in its required data rate R and time slot D. We also consider the time gap between two task blocks, that is the minimum and maximum time slot gap. And this page summarizes the main notations in this video. Especially, we introduce two decision variables, where X indicates the starting time slot and Y represents the processing duration. Then we can describe some K time slots by using these symbols. Considering the definition of decision variable X, the starting time for task J can be represented as follows. Based on the starting time, The finishing time slots includes an additional processing duration, that is the D here, and for the next task, J plus 1, the early starting time depends on the previous task finishing time slot, that is the theta F here, and the minimum time gap. And similarly, the latest starting time slot for task J plus 1 is determined by the previous finishing time and the maximum time gap. In the end, we could get an optimization model like this. In the objective function, R is the transmission data rate and Y represents the transmission duration. Therefore, this summation expresses the total transmission data on time slot T, and we use this objective function to minimize the peak aggregated data traffic rate. Constraint 5b gives the bound of the starting time for task J plus 1, and constraint 5c guarantees the last tasks should be finished within the period and keeps the minimum time gap. The next constraint 5d enforces that if the tasks start from time slot t, then the next d duration should also be set for processing purpose. In addition, the upper bound of the duration should be within the same period. Constraint 5e guarantees all tasks should be scheduled and only once. In the end, constraint 5f promises that the number of occupied time slots should be exactly match the processing durations. To linearize the optimization model, we introduce an auxiliary variable, that is Z here, which is defined as the peak aggregated data traffic rate. I'd like to point out that this model belongs to the family of NP-hard, which means solving it could be very time-consuming. So we provide a randomized search-based heuristic algorithm in the following page. By reviewing the optimization model, we notice that this constraint gives the earliest and latest starting time, and this constraint provides the latest starting time. So for the last task J, the latest starting time is determined by these two constraints together. Once the latest starting time for the last task J is determined, the latest starting time for the previous task, that is J minus 1 here, is also influenced by constraints 5c to leave enough time slots for the last task to be done within the time period. Thus, we have two latest starting time here. The first one is guaranteed the maximum time gap with the previous task, and the second one is to leave enough processing durations for the following tasks. Then we select the minimum of these two values as the real latest starting time. Once both boundaries, that is the early starting time and latest starting times, both of them are determined, one proper method is allocating each task in this area randomly. Subsequently, we rerun this process in several iterations and pick the minimum peak data rate assignment at the output. The detail of this proposed heuristic algorithm, which is called randomized time window preservation algorithm, is listed here. The details are listed here, and the time complexity of this algorithm is quadratic. Now, I'd like to move on to examine the performance of the proposed method. This table concludes the parameters we use for simulation. Here, we set the number of tasks per robot as 1, 2, and 3, which corresponds to the light, medium, and heavy-duty cases. The diagram on the right gives us an intuitive view of the performance, which comes from a heavy-duty case. Obviously, the yellow line, which represents the optimal solution derived from our proposed optimization model, holds very steady during the process and provides a smooth transportation. While the red curve is the proposed heuristic algorithm, whose value varies from 6 to 15 megabits per second. It contains some moderate fluctuations. And the blue one is not using any schedule method, and the data rate value changes heavily from 5 to 22 megabits per second. From the result, we can verify that the proposed two methods can be applied to flatten the peak aggregated traffic communications. We also estimate the peak data rate under several Monte Carlo iterations. In general, the proposed optimization model and the heuristic algorithm can provide better traffic allocations. Here we label the percent of the performance reduction, that is a POPR here in these three figures. The POPR is defined as the ratio of the traffic reduced rate compared with no scheduling. The light duty case shows a steady increase with the growth of the number of robotic manipulators from 2 to 10. In the medium duty case, the POPR has a rise from 2 to 6 and then remains steady after that. Furthermore, the heavy duty case reveals that the POPR saturates even with a small decline in value from 8 to 10 robots. What is interesting is that the trend of POPR performs similarly when we compare within the same number of robots. For example, when we fix the number of robots to 6, from light duty to medium duty to heavy duty, we find that the value is increasing and then goes down. So, I mean, here the trend of POPR performs similarly. One proper reason is that the POPR is affected by the number of robots and the number of tasks combinationally. When the value of robots and tasks are not large, all methods, including the optimal heuristic algorithm, even no scheduling, can find an allocation to avoid traffic congestion. Thus, the performance gaps among these approaches are not obvious. Then, with the growth of number of robots or tasks, the proposed method can find better allocations by placing the task blocks in the proper time slots, and thus the POPR increase accordingly. However, if the number of robots or the number of tasks is very large, the traffic congestion becomes inevitable, and even the optimal solution also suffers from the stacked peak data rate. Therefore, the POPR becomes saturated, even decreased. Having looked at the positive side, the positive part, I'd like to move on to discuss the side effects of the proposed author, especially for the optimal solution. We see the outperformance of the optimization model in peak data rate reduction is at the expense of more running time, which can be more than half an hour in some specific cases. And the proposed heuristic algorithm accelerates assignment and provides results within 200 milliseconds. In summary, from the view of performance, the optimal is better than the proposed heuristic algorithm, and no scheduling is at the end. Regarding the time complexity, it is in reverse order. So to conclude, in this video, I will show the method to optimize the communication peak data rate, which contains significant potential on capitalizing on the pseudo-deterministic traffic profile in industrial networks. In particular, the proposed schemes can reduce peak data rate more than half compared to no scheduling scenario. And this traffic reduction has significant ramifications on network slicing in industrial networks, since more efficient allocations can be performed. As a future work, we consider augmenting the model with AI so that it can learn patterns autonomously, then optimize industrial networks. That covers the main points. If you have any questions, I'll be happy to answer them. Thank you, and 감사합니다.